In this segment, we'll talk about how do we write simultaneous linear equations in matrix form. So let's suppose somebody gives you the following simultaneous linear equations. So when somebody is giving you three simultaneous linear equations, and let's suppose they say, hey, can you write this in the matrix form? We seem to automatically jump to this. If I asked students to do this, they will simply start writing like this. They'll say 25, 5, 1, 64, 8, 1. You got to understand the coefficient of C here is 1, not 0, just because there's nothing there. 144, 12, 1, they will say A, B, C, and they will put 106.8, 177.2, and 279.2. But the thing which we have to realize is that how do we get from here to here? That's not a direct step going from here to here. It might come to you as a direct step once you have a lot of experience with it, but there's a lot of things which go beyond before you get to this level. So what are those steps? Is that what I can do is I have these three simultaneous linear equations, so each one of them is a separate equation, and what I'm going to do is I'm going to put them in this kind of a matrix. I'm going to say, hey, I'm going to write 25A plus 5B plus C right here, and I can put 106.8 here, and I can say 64A plus 8B plus C here, and I get 177.2 here, and I get 144A here plus 12B here plus C here, and I get 279.2 here. So what I've basically done is that I have put these three simultaneous linear equations in some sort of a matrix form where I got 3 rows in one column and 3 rows in one column right here. And I can rewrite this now. I can say, hey, what I can do is now I have written it like this, but if I write 25, 5, and 1, so I'm trying to separate out the unknowns here. If I write 25, 5, and 1 here, I could write this as A, B, and C. And if I write this A, B, and C, you can very well see that if I have 25, 5, and 1 and multiply it by this vector A, B, and C, I'll get the first row, first column, this part right here. Same thing here, 64, 8, and 1. When I multiply 64, 8, and 1 by A, B, C, by this row vector, by this column vector, I'll get this second row, first column of this matrix here. And same thing, I do 144, 12, and 1. If I multiply this row vector by this column vector, I will get this third row, first column right here. And you can see that this is the 3 rows, 3 columns, and this is 3 rows, 1 column. And when I multiply 3 rows and 3 columns by a vector which is 3 rows and 1 column, I get 3 rows and 1 column right here. Will be equal to 106.8, 177.2, and 279.2. So it's important to understand that, hey, we go from this to here, and then from here to here through matrix multiplication. This is equal to this is based on when do we consider two matrices to be equal, when element to element they are the same. This element right here is same as this element as given by the first equation. This element here is same as this element here as given by this equation, and this element here is same as this element as given by this equation. You also need to recognize that, hey, these equations can be, or these equations right here can also be written as a linear combination. Like I can put A here, and I can put 24, 25, 64, and 144 here, plus B times 5, 8, and 12 here, plus C times 1, 1, 1 here, and that will be equal to 106.8, 177.2, and 279.2. So you can look at these three equations, three unknowns also as that, hey, these sets of equations can be written as a linear combination of this vector, and this vector, of the linear combination of 3 column vectors equal to this column vector. and whatever linear combination of A values of A, B and C which will satisfy this linear combination to be equal to this value, this vector here right here will be the values of A, B and C. So you have got to keep an open mind in terms of recognizing what it means to convert a set of simultaneous linear equations into a matrix form. And that is the end of this segment.